All right, so differential fields. Again, nice little review of multivariable calculus. We won't get too much into these type of curves and these type of graphs, but just brief introduction before we get to the main stuff. So this section is about the same as multivariable calculus, like I said. Um, Now, depends on who you are. This is either called slope fields or vector fields. Um, they go both in cases. Technically, a slope field is in 2 dimensions, is what we have here. Vector fields are in 3 dimensions, but you can still technically do the vector field in 2D. So it's just one or the other. It really doesn't really matter how you call it itself, um, because in either case, it's a solution to a differential equation, right? So it's not like it's not not different from each other. Okay, so usually you have this portion, you graph the differential function using a t-chart itself. And so, for example, here we have a grid of a 2 by 2 situation. So 1, 1, 2. And all we want to do is find equations or find graphs that satisfy these equations. And you kind of like follow this pattern as best you possibly can. You're just going to follow the lines, little jagged lines, and you eventually see they kind of look like this. And again, these are not all of them, but these are some of the differential equations that I would work, right? So all of these functions, lines, will satisfy this differential equation. Okay. Well, again, where all of these are the arbitrary c values themselves, right? All at different levels. So we're not going to do too crazy. It's just understanding what a graph represents to the actual function. So for the population p in thousands at time t of a certain species is given by this equation. Okay. From the differential field given, so using our differential field, let's answer these questions. So the first one is, if the initial population was 3,000, what can we say about the limit as t goes to infinity of our function? Okay, so we have initial condition at 3,000. So if you go up over here, this is 3,000 right here, right? So the thousands. And we can do the same thing I was talking about up here. We're just going to follow a process and see where that actually lands. Okay. So what that means is, okay, so if I just follow the flow from this point, and eventually it flattens out. So as I take this limit, it looks like it's just going to reach 2,000. Right? It just flattens out. Remember, again, little review of what calculus writes the limit just as what is the y value eventually when the x value or the t value just goes to infinity forever, right? Part B, can the population of 100 ever decline into 500? So again, saying if the initial condition was 100, 1,000, which is right here. Again, if I follow this portion, it looks like it's going here again. But my question is, will it decrease to 500? So 500 is halfway here. So in other words, will it ever touch this part at all? And again, if you follow this format, it never goes down. So this will be no. It only increases and maxes out at 2,000 there. And last question is, can a population of 1,000 ever increase to 3,000? Again, it's a bit of a trick question because, again, if you just follow this template we have here, you can say, well, the limit as t goes to infinity of this actually is, again, 2,000 because it flattens out. Well, if the limit goes to 2,000 and that's all it goes to, as long as it just forever, it can never reach 3,000 because, again, it will never cross this threshold at all. So this is no. Okay. And the last little definition of this section is, okay, quick little section, is a differential equation that only has a dependent variable in its equation is called an autonomous equation. Okay. So only a dependent variable into it. So in other words, like this. We don't have any t in it, right? It's strictly just the dependent variable. So this is called an autonomous equation.